Now let's look at the half adder and the full adder in CMOS. Now we'll do a comparison with the NMOS circuit which we've seen in a previous video. So we'll start off with the truth table that we have here. So we've got our A and our B inputs and we're going to add them together. We've got our sum and our carry here, and we've got the complements of the sum and the carry here as well. So we wanted to generate a sum and a carry, but we know from the NMOS pull down logic that we can generate the complement of the sum and the complement of the carry, and that's the complement of the sum and the carry here. So that means that rather than having this sum, which is going to be an exclusive OR gate, and the carry, which is an AND gate, we're going to have an exclusive NOR gate and a NAND gate, and then the outputs will go through an inverter, which will give us our final sum and carry. So we've seen that in the previous video. And in this instance here, we're going to first of all look at the sum function. In the next page, we'll look at the carry. So in the sum function here, we're going to have the exclusive NOR gate here, and then we're going to have the inverter. Now I'm not going to talk through this exclusive NOR gate because we've talked through it in the previous video. Now what we want to do is we want to take this sum in NMOS and we want to generate it in CMOS. Now we've seen from the previous videos that we're going to have a pull-up network, which will be in PMOS, and a pull-down network, which will be in NMOS. Now the pull-down network here is the same as the pull-down network here. It's just an NMOS devices, which will give us the function that we require, which is going to be given by this little block here. So now if there's anything here in this page that you really want to understand, it's this little section here, because this is going to tell us how we build both our pull up network and our pull down network. So in case of the pull down network, although we've already talked about it, we'll just talk about it and we'll see how we can generate it directly via the truth table. So if the output is a 0, then the pull down network is required, in which the inputs are going to be the Boolean functions given by our A's and B's. So let's put that into practice. So the output is a value of 0. So the output here is the not sum we're dealing with. So the output is a value of 0. So that's here and here. Now the inputs are going to be the values given by A and B in this case. So we're going to have not A dot B. So that's not A and B, which are going to be in series. And we've got our not A and B here. And those are going to be in parallel with A not B, and that's our A not B. So this one is in parallel with this one, and each of them here are in series. So the not A B is in series with the A not B. So that's just given us the same network that we've seen, but we're able to generate it directly from the truth table. Now we're also going to have the pull up network, and you can see here that if the output is a value of 1, then we're going to need a pull-up network, in which the inputs are going to be the Boolean complements of A and B. So let's have a look and we'll see how we're going to generate that. So in this case here, the output is 1 here and output is 1 here. In order to generate this one, we're going to have to take the Boolean complements of these. So the Boolean complement of this is 0, 0 is going to be 1, 1, which is just going to be a value of our A and B. So that's our A and our B here. Now this other one here, the output of 1, is going to be the Boolean complements of these here. So that's going to be 0 and 0. So that's going to be our not A and not B. So we're going to have A and B in series, and both of these are going to be in parallel with not A and not B. So that's how you read off the truth table and generate the actual function here. Now don't worry too much if you didn't follow all of that completely. We will be going over a few other examples. So next we'll look at the carry section for the CMOS adder, and then we'll look at the full adder. And over the next few videos, we'll look at generating the circuit diagrams from the truth tables. And you'll soon get used to using it, and it'll all become quite simple for you. So let's go ahead and we'll look at the carry section. So here's the carry section for the NMOS logic, and we've seen this in a previous video. So the carry section is nothing other than our NAND gate followed by an inverter. Now the NAND gate in CMOS logic is given by this function here, so we're not going to talk through that. We've seen that several times before. And then it's the inverter is the NMOS inverter, and again we've seen that previously. Now what we want to do is we want to change this function into the half adder for the carry for the CMOS. Now again, it's going to be a pull up network and a pull down network. Now the pull down network, again here, if we were to read it off of the truth table here, we could say that if the output is 0, then it's a pull down network. And the inputs are the Boolean functions given by the inputs AB. So for example here, if the output here for the carry is 0, so that's this one here, the output is 0, you can see that both the A and the B inputs have to be high. So that's going to be our A dot B, so that's AB in series, so that's our A and our B in series. So again, that's just the same pull down network that you see here for the NMOS. So the pull down network for the CMOS is just going to be the same as the NMOS. Now what we're interested in is the pull up network. In the case here, it says that if the output is a 1, then the pull up network is required, in which the inputs are the Boolean complements of AB. So you could have a look at this one here. We can say that we're now looking at the carry here, that's the not carry, and we've got 1, 1, 1, and we could say that we're looking at the complements of this. So the complements of this would be actually, in this one's case here, that would be AB, and then we would have the, in this case it would be A not B, and then it would be A not B. So you could write down the full Boolean function for that, and you could work through the Boolean algebra. Now I suppose I could do a little section of it here. So you're going to have, in this case here, the high output, so you're going to have the complements of the inputs. So the complements of the inputs are going to be the AB, and that's going to be ORed with the complements of the next input, which is going to be, well, that's going to be A not B, A not B, and finally the complements here, that's going to be the value of not A B plus the not A B. So we could take out the common factor between the first one and the third one, which is going to be the value of B. So we could have a B, and then you would have A for this one, plus, in this case here, we would have not A, and then we'd be left with the centre one, which is going to be A B naught. A plus A naught is just a value of 1, so that would be B plus A B naught. Now this thing here is nothing other than A ORed with B. So just to check that out, you could always put in the values for the truth table for A and B and B naught, and then work this out, and you'll see that this here is just the same as A ORed with B. And that's like what we have up the top here. We've got our A ORed with the value of B. Now we didn't need to go through all this process here. I just wanted to go through it this once just to show you that this does actually work then within the purple box, so the pink box. So if you're ever stuck, you can always revert to that. But we do know what a NAND gate looks like, and we talked about it in the previous videos, and we know that in this case here what we're going to do is we're going to take the series combination and make them parallel combinations. So rather than working through all of this, we could have just looked at this and says, well, these are two are series here, so we'll just make them in parallel here, and this would be us have our half adder for our CMOS. Of course, we'll have a half adder once we've actually added in the inverter at the end here, which is the inverter here for the carry. So that's the half adder. I think what we'll do is we'll finish this video off because it's getting a bit longer now, and we'll go on in the next video and we'll do the same for the full adder in CMOS. So thank you for listening. I'll get you in the next video. Goodbye.